Hello viewer. In this video, we will learn about temperature entropy change, that is TdS relation. We will learn about the significance of temperature entropy plot now. For that, we are going to represent a process in a TS diagram. And y-axis it is a temperature, x-axis it is the entropy, and 1 to 2 is the process, and 1 is the initial state of the system, 2 is the final state of the system. When the path followed by the change of state is completely defined, then we can say the system has undergone a process. So 1 to 2 is a process. Suppose if we want to calculate what is the heat transferred during the process 1 to 2, then we make use of the relation ds is equal to dq divided by t. This relation can be rewritten as dq is equal to tds. This is a differential form. And to calculate the heat transfer between the end states 1 and 2, we need to integrate this equation. So upon integration, this yields q is equal to integral 1 to 2 TdS. What is this integral TdS? With respect to this TS diagram, integral TdS between the limits 1 and 2 is nothing but the area under the curve. Therefore, what we infer is area under the curve in a TS diagram represents heat transfer. We know area under the curve in a PD diagram represents work transfer, whereas the area under the curve in a TS diagram represents heat transfer. In order to integrate this equation, we need to know the relation between TdS. Suppose if this process is reversible and adiabatic. What is adiabatic? In which there is no heat transfer. Then change in entropy ds is equal to 0, and that process is called isentropic process. So dq equal to 0. Why? Because it is reversible and adiabatic. Therefore, a reversible and adiabatic process is called as isentropic process. What is the entropy change when the temperature is constant? We can take out temperature is constant, or we can take the temperature out of this integration. What is left out is integral ds, which is for an isothermal process, entropy change ds is equal to T multiplied by S2 minus S1. So for a reversible adiabatic process, entropy change is 0. For isothermal process, entropy change is T multiplied by S2 minus S1. What is the entropy change during constant pressure process, constant volume process, or in general a polytropic process? We will learn how to calculate the entropy change now. Now, to study this TdS relation, we know first law for a process in differential form is equal to dq minus dw is equal to change in internal energy. What is this dq? Just now we discussed dq equal to TdS, and in the absence of other works, or if only PdV work is considered, dw is equal to PdV. Substitute these two things, we will get TdS. So instead of dq, we substitute TdS, and instead of dw, we substitute pdv. We will get like this. This can be rearranged in this form, and this equation is called Gibbs equation. TdS is equal to TdQ plus pdv. Also, we know enthalpy H is equal to U plus PV, and in differential form, this equation takes this. dH is equal to du plus pdv plus vdp. So this pdv plus vdp is nothing but differentiation by UV method. Now consider this equation. Instead of this du plus pdv, we can substitute TdS because TdS equal to du plus pdv. Therefore, this equation dH can be written as dH is equal to TdS plus VdP. So this VdP comes over here. Instead of this TdS. This can be rearranged to give TdS is equal to dH minus VdP. Now, there are two equations for TdS. TdS equal to du plus pdv. Here, TdS equal to dH minus VdP. And these two equations gives change in entropy. ds is equal to du by t plus pdv by t, or change in entropy ds equal to dH by t minus vdp divided by t. To calculate the entropy change, we need to make use of these relations. We will discuss what is the entropy change for ideal gases. Just now we discussed what is the equation for the change in entropy, TS, using TdS relation. For specific entropy, those equations are written like this for specific entropy change. That means per unit mass, ds equal to du by t plus p dv by t. So this v is specific volume, this u is specific enthalpy, here h is specific enthalpy, specific volume. So we get two equations. Bifurcate the strain into two. We know du is equal to Cv dt and Pv equal to RT, and this can be rearranged like this. Therefore, instead of du, we can substitute this. Instead of P, we can substitute this. Meaning, so instead of du, substitute this. Instead of, can substitute this. And upon substitution, we get like this. And here this T gets cancelled, and this equation is rearranged like this. And to calculate this entropy change during the process 1 to 2, we need to integrate this equation. So S2 minus S1 is equal to integral 1 to 2. Cv is a constant, dt by t plus R is a constant, dv by v. So to integrate, we need to know what is the relation between this one, or it's a simple integral. What it yields is this equation. Similarly, we can calculate entropy change for this relation also. Again, same method. Here instead of du, we have dH. We know dH is equal to Cp dt, and Pv equal to RT and V equal to RT divided by P. Once again, instead of dH, we can substitute Cp dt. Instead of specific volume, we can substitute RT divided by P. On substitution, it yields change in specific entropy is equal to this one, which can be written like this. And to find the entropy change, we need to integrate. Cp is constant, take it out. R is a constant, take it out. So what it is integral 1 to 2 dt by t, dp by d. We can integrate directly. S2 minus S1 is it will give after integration this equation. Therefore, to calculate the entropy change during a process, we can make use of any one of these two equations. And this entropy change equation is obtained from TdS relation. Thank you.